सादर नमस्कार, सुस्वागतम, अभिनंदन, केम छो, जय श्री कृष्णा, वणकम, आदाबर्स, सत श्री अकाल, कंबागड़ी, राम राम, राधे राधे, वेरी गुड मॉर्निंग। मैं अनिल भारद्वाज आप सभी का पीआरएल के अमृत व्याख्यान में स्वागत करता हूं, अभिनंदन करता हूं। आई अनिल भारद्वाज वेरी वार्मली वेलकम यू ऑल टू पीआरएल का अमृत व्याख्यान। Today is a historic PRL Amrit Vyakhyaan for three reasons. First, today is the 101st 101वां PRL Amrit Vyakhyaan. We started the PRL Amrit Vyakhyaan as a part of celebration of PRL's Platinum Jubilee and completing 75 years of establishment, established by Dr. Vikram Sarabhai. And we took a sankalp on 4th of August 2021 that every Wednesday, every week at 4 p.m., we will have PRL Amrit Vyakhyaan. This sankalp got completed on 5th of January 2023 when we completed uninterrupted 75 episodes. And then we started the PRL Amrit Vyakhyaan 2.0 with another sankalp that every month we will have one Vyakhyaan. And today we are completing the silver jubilee of PRL Amrit Vyakhyaan 2.0, that is 25th episode of PRL Amrit Vyakhyaan. So it's a double bonanza that it is 101st PRL Amrit Vyakhyaan and 25th PRL Amrit Vyakhyaan 2.0. PRL Amrit Vyakhyaan, as I just told, is to celebrate the PRL ka Platinum Jubilee, but also to celebrate the history and legacy of PRL in the area of physics and space sciences. Today, the third reason for this is that on 18th of February 2025, that is today, we have a very, very distinguished Vyakhyaan with us, Dr. V. Narayanan, Secretary Department of Space, Chairman ISRO, and Chairman Space Commission with us, who promised me on phone that I will come for the 101st PRL Vyakhyaan, and he kept his promise to be here today with us for this. So, sir, we are truly humbled and delighted to have you here in PRL campus in this auditorium named after Dr. K.R. Ramanathan, who was the first director of PRL, and Dr. Sarabhai, who is over here as the person who established PRL. Dr. Narayanan would be delivering his Vyakhyaan on the topic Propulsion System for Launch Vehicles and Satellites, which is a hardcore system which is required for any launch vehicle and satellite to be successful. And he is there for last 4 decades in ISRO, serving to the nation in his different capacities. So I will now request my colleague, Professor Pallam Raju, who is the Dean PRL, to formally introduce Dr. Narayan. Of course, he doesn't need any introduction, but we have very large number of youngsters in the audience, and many of them have joined on the YouTube channel of PRL, so that they are aware about the accomplishments of Chairman ISRO Secretary DOS, as well as to formally introduce the today's Vyakhyaan Karta. So I will now request Dr. Pallam Raju to introduce Dr. Narayanan, and I will take leave from you. Thank you. Dhanyavad.
A very good morning to all of you. It's a full hall here. It's an amazing sight to see. It is indeed my pleasant duty to introduce the Vyakhyaan Karta of the 101st PRL Amrit Vyakhyaan, is Dr. V. Narayanan, who is coming here after assuming charge as Secretary Department of Space and Chairman ISRO and Chair of Space Commission to to address us. Dr. Narayanan did his MTech in cryogenic engineering at IIT Kharagpur, and later on did his PhD from IIT Kharagpur in 2001. But soon in 1984 itself, he joined Liquid Propulsion System Center, LPSC, wherein he has contributed immensely in various aspects of propulsion systems. Dr. Narayanan is a rocket and spacecraft propulsion expert and served in various capacities in the various areas of solid propulsion of solid sounding rockets and ASLV, Augmented Satellite Launch Vehicle, and PSLV when he was at VSSC, wherein he contributed immensely to the aspects of process planning, process control, and realization of ablative nozzle systems, composite motor, and composite igniter. As one of the few members working in the cryogenic area from its real inception or initial stages, he carried out fundamental research, theoretical and experimental studies, and contributed to the successful development and testing of cryogenic subsystems, namely gas generators, subscale cryogenic engine of 1-ton thrust, and chamber of 12-ton thrust. And further, he moved on to, he played a crucial role in the successful deployment and development of the indigenous cryogenic upper stage and contributed to making it operational in the GSLV Mark II vehicle. Further, Dr. Narayanan contributed in establishing the necessary infrastructure and facilities for design, analysis, realization, testing, and launching of the GSLV Mark III vehicle. Due to his innovative approach, the C-25 cryogenic stage was developed under his guidance in the shortest time frame and was inducted into the GSLV Mark III vehicle. His contribution made India among one of 6 nations which have the complex and indigenously developed propulsion system and achieved self-reliance in this high-performance cryogenic propulsion systems. Again, as the chairman of the National Expert Committee constituted to study the reasons for hard landing of the Chandrayaan-2 lander, he contributed to pinpointing the exact reasons for this occurrence and suggested corrective actions required to overcome this challenge. And as we all know, that resulted in a successful landing of the Chandrayaan-3. And this made India one of the 4 nations which is capable of landing on the moon, in soft landing on the moon. He has received numerous awards. Some of these include Gold Medal from Astronautical Society of India, ASI Award for Rocket and Related Technologies, Team Award from High Energy Material Society of India, Outstanding Achievement and Performance Excellence Award, and Team Excellence Award of ISRO, Distinguished Alumnus Award 2018 by the IIT Kharagpur, National Design Award 2019 from the National Design and Research Forum, and National Aeronautical Prize from the Aeronautical Society of India. For his various contributions, Dr. Narayanan has been elected as a member of the International Academy of Astronautics, Fellow of the Indian National Academy of Engineering, member of Space Propulsion Committee of International Astronautic Federation, National President of the Society of Systems for Science and Engineering, Fellow of Institutions of Engineers India, Fellow of Indian Cryogenic Council, and Fellow of Astronomical Society of India. He is a member of Governing Council of several institutes and engineering colleges in the country. And today, he's going to talk to us on the propulsion systems for launch vehicles and satellites, and especially with the Chandrayaan-4 and Bharati Antariksh Station and the landing on the moon programs coming up in the near future. It is really essential that we should have the vehicle that can carry the load of several tons of the vehicle load. So I think he and his team is going to play an immense role in this, and I'll really invite Dr. Narayanan onto the dais to please tell us on the propulsion systems and how we are gathering our energy and momentum to really cross the limits to go to higher altitudes. Dr. Narayanan, please put your hand together. Okay. Right. Not at all. Don't worry. Very good morning to all of you. Dr. Anil Bharadwaj, Director of PRL, and my very close friend. Our association is more than something around 30 years plus. And Dr. Pallam Raju, who is the Dean of this great institute, and the faculty members, scientists, senior scientists, and students of this great institute, PRL. I consider this as a great honor and privilege to be along with you after taking over as the chairman of ISRO and secretary of Department of Space. Really, I have to thank the PRL director for giving me this great honor to give a talk. The 101st talk of PRL's Amrut Vyakhyaan talk. In fact, he was going on asking me a couple of times, almost 2 years back, 2 to 3 years, he is behind me to get me here for giving the talk. But then for everything, I feel there is a right time which has to come. And I really, you all know, before I go for my talk, after taking over as the chairman, ISRO on 13th January afternoon, I was going around the country to take the blessing of elders, to request the youngsters for their prayers for us to take the organization to greater heights. And in that context, I am so blessed today. We have taken the blessing from, of course, yesterday itself we took the blessing from our visionary leader, Sarabhai ji, and that too taking the blessing from the place where he operated and the entire space program was put in place. That's a great blessing, I consider. And I know I am standing in a place which is historically important. I need not explain to this audience. You know, the Indian space program was started in the year 1962 by none other than our visionary leader, Sarabhai ji. And from that time onwards, we have come a long way. It was in the year 1967, November 20th, we had the first indigenous rocket which took off from Tumpa soil. And before that, 1963, November 21st, we had the first rocket launch from Indian soil. Until 1975, we were not having our own spacecrafts. It was in the year 1975, we had the first spacecraft built with the support of others, which took off from Indian soil, the Aryabhatta, not Indian soil, launched by other country, but built in this country with the support of others, 1975. Now, if you look at the growth of the Indian space program, to summarize, a country which was not having a rocket launch vehicle technology, and till today, we have from 1979, we placed the first launch vehicle was launched, and from that till today, we have developed 6 generations of launches, and the 100th launch took place on 29th of January, and it was a very grand, successful mission. I think we all can be proud. And in the area of satellites, you all know, till today, 131 satellites are built. Varieties of satellites are built, and the heaviest one being the GSAT-11, the high throughput satellite of 6,000 kg, which is placed in the orbit. And almost more than 4,000 sounding rockets have taken place from this place, from India.
Also, approximately 433 satellites of 35 countries, which is lifted off from Indian soil using Indian launches. So it's a great accomplishment. And all these rockets and satellites are for what? For serving the common man of this country. I think I'm not going to get into that. You know what are all the applications. We are serving the country in a very big way, technology-wise, and for making, ensuring the countryman's happiness and welfare, security, every purpose it is serving. Now coming to the PRL, I think 1963 when the first rocket took off, the contribution goes back from that to January 6th, we rolled out the data for Aditya L1. I think everywhere your hands are there. So let me really give great appreciation for that. Now, when you look at a country, when we started with the 1 meter height rocket in 1967, that time, 1961, Yuri Gagarin has gone to space and he's brought back safely. 1969, I still remember I was in the first standard sitting on the floor studying with a couple of my classmates, and our teachers announced that man has landed on the moon. And we were not even LKG standard level. Let us be very frank. We are 60 to 70 years behind the advanced countries. And today, to our credit, lot of accomplishments. Take Chandrayaan 1, I think I was putting a question to your director. He nicely answered. Who found so many sample return mission has happened, but who found water molecules on the moon? And really, it is a great honor to all Indians, and all of us can be proud. And PRL has got significant contribution towards that type of discoveries. And Chandrayaan 2, Chandrayaan 3, Aditya L1. I think I am not going to dwell on your contribution. I can talk 1 hour on that. Then by the time he will give me a paper stating that your time is out. So I am not going to venture into that. Dear friends, in nutshell, the contribution of PRL is so significant, and you are going to contribute. We are going to work together, and you are going to contribute for taking this country to much greater heights and contribute for making this country as a developed country before we celebrate the 100 years of independence. I request all of you to work together. We will work together, and we'll take this country to greater heights. Now, coming to the today's talk, it is a great honor. The 101, that is a great number. And just we have completed 100th rocket launch, and 101 launch, we are getting ready. And at that point of time, I am so blessed and privileged to deliver the talk of the 101 talk. Now, we were discussing what is the topic. As a chairman, I am supposed to talk general programs and what it is and what we are supposed to do. But then I thought it is a highly educated mass. You all know what it is. And then my friend suggested, sir, we want you to, Narayan, we want you to hear your core field of the propulsion. So then I thought better to converge on that core field. I know it is a small field, but doesn't matter. I have converged on that field. So that is the thing what is selected, the propulsion systems for launch vehicles and satellites. Before I go to the talk, let me tell you one thing. What is the difference between the rockets, crackers or rockets, what we use during the Deepavali time and the launch vehicles? I will tell my recent experience. Last Deepavali, we are a little elder people, we don't fire too much crackers. So I happened to cross Madurai area, so we bought a lot of crackers. And I bought almost half-meter size, 12 rockets I bought. So we are in a campus. There is apartment, 9-story building apartment and 11 houses. So after doing something, so first rocket I took, and to be frank, I prayed well. When my son told no, he will not do it because a lot of people are there. Then when I really gave that flame to that, I was praying that it can go anywhere. It should not go to that apartments. Because if it enters there, it is a social problem, everybody will blame me. That too, a rocket scientist, a director of a center, and firing rocket into somebody else's house, it will be a social problem. No, you believe me, with so much care, this was done. You know what happened? This rocket went here and there, finally reached the 9th-story building. 9th floor. My wife was so furious. What is that you are doing? And you are a space scientist and you are firing rocket to somebody else's house. I am telling you, before the neighbors came out, I bundled all the rockets and I gave it to my wife, and it was put into the house. We came back and we never attempted. So the fundamental difference between the Deepavali rocket and our rocket is a simple difference. Deepavali rocket, the Sivagasi or wherever it comes, after some 20% time it will not work. Even if it works, it will go wherever it wants. But our launch vehicle should go wherever we want. That is the only small difference. Towards that only we all are working. You know, that to make that small difference, you know, how much work has to be done. Navigation, guidance, control, proper propulsion system, mission planning, then everything has to be done. Now, this slide shows the accomplishments of ISRO in a nutshell. And whatever I have explained, I think everything is there. I'm not going to dwell on that. And we have got lot of accomplishments and achievements. Now, when you take a launch vehicle or rockets, there are so many systems are there. And one of the very, very important and critical system is the propulsion system. Propulsion system is the one which gives the required muscle power for the rocket to take off from Earth. And that is the first step. It has to cross the dense atmosphere and go to the required place. It gives the muscle power. And there are two types of propulsion system. One, we call it as Earth to orbit propulsion system, what is used in the launch vehicles. And another one is the space propulsion system or in-space propulsion system, which is used in the satellites. Now, these slides give only one idea. You know, the launch vehicle, you take a Mark III vehicle. Out of the total liftoff mass, 98.3% is the mass of the propulsion system and propellant. That shows the capability or ability of any launcher is dictated by the capability of the propulsion system. Of course, other system I don't underestimate, but everything is important. That too, as a chairman, I cannot speak only on propulsion. So every system is equally important, but this plays a crucial role. Then coming to the chemical propulsion system, take Chandrayaan 3 as an example. Here I have put GSAT 11, you can read the numbers. Out of 3,950 kg, if I'm correct, the Chandrayaan 3 spacecraft, 3,013 kg is the propulsion system, the engines and propellant, what is used for taking to moon then and landing. That speaks volume of the propulsive system. Now, for whenever I go to the village school, you know, generally when you talk about a propulsion system, we have to really understand what it is. The propulsion system or the launch vehicle propulsion system or engines, the functional requirement is very simple. What is the car engine? What it does? The car engine assists to take either human being or objects from one place to another place. Am I right? That is the purpose of a car engine. Same way, the launch vehicle propulsion system is used for either taking satellite or human being from Earth to orbit. And of course, sometimes we have to bring back them. Some of the things we have to bring back. But there is small difference. With respect to function, it is same. Car, even Ahmedabad, what is the maximum speed at which it can go in Ahmedabad road? Maybe 100 km per hour is the type of, or 80, or less or 60 km per hour. Let us put that numbers. And to place Chandrayaan 3 in the orbit, we have to give 37,000 km per hour is the velocity we have to give. Against 80 or 60 km per hour, this has to do that job. That makes the propulsion system little different. Now, you can work out. I think we have studied in the high school in a petrol car. There is a part called the carburetor. I have studied in my 7th standard, which is used for mixing air, petrol with a ratio of 3:1 or 3.5:1. And now you can do some fundamental calculation per liter, how much kilometer will go. And from that type of thing, you can do a calculation per second. Something around 3.5 to 4 gram per second is the consumption in a car, fuel air consumption. Against that, when a Mark III lifts off, we consume something around 4,200 kg per second, at 10 power 6 times. That is the type of difference. Now, I will give another thing, aircraft engine. You take an aircraft engine, to generate a 20-ton thrust in the aircraft engine, 1000 kg per second of air plus aviation fuel is used. You talk about a cryogenic engine, what we have developed, C25 engine, it generates 20-ton thrust using 45 kg per second of fuel. That means you can understand what is the energy intensity and how you have to extract the energy. That makes the propulsion system more complex, and we call it as a energy intensive system. Again, in terms of power level, you can see 88 horsepower is the car engine power. And when it comes to SSME, 3 engines, it is something around 37 million horsepower. That is the type of power level difference. Now, coming to the launch vehicle propulsion, there are different types of propulsion. Basically, we use chemical propulsion for the launch vehicles, depending upon the state. It is classified as liquid, solid, or hybrid propulsion. Again, liquid, monopropellant or bipropellant system. Again, depending upon the nature of the propellant, it is called storable, cryogenic, or semi-cryogenic propellant. Storable is in the atmospheric condition, the propellant will be in the liquid form. Cryogenic, by definition, the propellant will be at much lower temperature, minus 150 degrees centigrade and lower. And hydrogen, minus 253 degrees centigrade, liquid hydrogen gas will be in the liquid form. And you can understand such a low temperature hydrogen gas, hydrogen liquid. And oxygen is used in the cryogenic area. And semi-cryo, oxidizer will be in the liquid form and fuel will be in the air storable condition. And again, the selection of the propulsion system is depending upon a lot of parameters. I cannot dwell on that, depending upon the thrust requirement, total impulse requirement, and the performance parameters like specific impulse. Specific impulse is the thrust generated by per unit weight flow rate of propellant. And density impulse, thrust generated per unit volumetric flow rate of propellant. So this decides. Then of course, reusability, low cost. At the end of the game, it is the core competence of the team which develops the propulsion, which decides what type of propulsion one has to select. And of course, we have developed a lot of things. And I think one parameter you can easily understand, the specific impulse, which is a performance parameter. It is nothing but, equation is very complex equation, but in a simple form, root T by m bar is the performance parameter. Root T is the combustion temperature, m is the mean molecular temperature, mean molecular weight of the propellant combination. And hydrogen being a low molecular weight, you can see the numbers, the cryogenic propulsion is superior in terms of performance of ISP, and whereas density impulse, it is not that superior. And all the numbers are here, probably I'm not going to dwell on those things. Now coming to the space transportation fleet, as I told, we have developed almost 4,000, we have launched something around 4,000 plus sounding rockets and 6 generations of vehicles, and the capability, all these things are there. The SLV is the first rocket, rather launcher. The capability was 40 kg to low Earth orbit, and Bahubali rocket Mark 3 is something around close to 9,000 kg to low Earth orbit, and we have developed host of launches. And these are all the operational vehicles, the PSLV, GSLV, Mark 3. And in the SLV and ASLV we used only solid propulsion system. And in the PSLV, for the first time, the air storable liquid propulsion along with the solid propulsion was inducted. And GSLV, we have inducted along with air storable propellant plus the solid motor, we have also used the upper stage as the cryogenic propulsion system. And Mark 3, we have got all the 3 types of propulsion systems. Now, small satellite launch vehicle, here, mainly it consists of the solid propulsion system, and only the velocity trimming module, the upper stage is the liquid propulsion system. Now, coming to the solid propulsion system development in the country, actually, this itself can be a topic one can talk 2 hours. So I have put only one slide. So now the entire game started 20th November 1967 with the small rocket launch with the solid propulsion. And basically, the propellant is in the solid form. And from that, a lot of development has taken place. The heaviest motor ever built in the country is the S200 strap-on motor of the Mark 3, which is having 207 tons of propellant loading. And of course, there are so many motors till today we have developed. And I have given a comparison, the heaviest or largest motor ever developed in the world is the USA. And the thrust level is something around 16,000 kilonewton. And Mark 3, the solid motor is something around peak thrust is close to 700 kilonewton. and 7,000 kilonewton, and ISP is the number given, and then the propellant loading against our S200 207 ton, this is 630 ton is the propellant loading. And there are varieties of solid motors are developed, including the crew escape system motors, which are all fast burning motors. In case of the crew Vyakhyaan program, anything happens, any problem happens to rocket, the crew should be saved safely. So including those things, we have got a lot of developments. Coming to the liquid propulsion, the major advantage compared to the solid propulsion is the repeat use of the engines. You can test the engine and you can fly. And when the required velocity reaches solid motor, once you fire, till it completes its performance, you cannot stop. Whereas here, the moment you get the required velocity, you can stop, restart. Lot of advantages are there, and performance is also superior. But then it is really very, very complex compared to the solid propulsion. And the entire activity in the world, if you take 1921, it all started. And 16th March 1926 was the first small firing. From that till today in the world, almost 1,300 plus engines are developed, but everything is not flown. And to our credit, you can see 1969, when man has landed on moon, the world has developed huge rocket engines, and we tested a small thruster, 5 kg thruster. From that, today, to our credit, lot of engines are developed, starting from 1 Newton thrust to the Vyakhyaan engine, 800 kilonewton thrust. And the largest engine, what we are developing is semi-cryogenic engine, which can develop 2,000 kilonewton or 200 ton thrust. And I have given one comparison where the world was. For the moon landing program, the Russians developed an engine called RD-270 engine, 6,270 kilonewton, which is compared to our Vyakhyaan engine, Vyakhyaan is only 800 kilonewton. This is the type of thrust that people have developed elsewhere. And coming to the air-storable system, we have developed for PSLV the Vyakhyaan engine. It's a air-storable using air-storable propellant. And PS4, the upper stage is powered by 2 pressure-fed engine. These 2 engines we have developed. And the heaviest stage ever built by the air-storable stage built by our country is the Mark III core stage, which is powered by 2 Vyakhyaan engines, generating something around 800 into 2. That is the type of thrust it is generating. 800 kilonewton into 2. That is the type of thrust it is generating, and the propellant loading is 110 tons. And till today, 7 stages are realized and successfully used in the flight. Coming to the next important program, the cryogenic propulsion system. It was in the year 1991. We conceived the Mark III vehicle with the upper stage as the cryogenic propulsion stage. And in fact, we all know from the literature, people have taken more than 15 years for the development. So at that point of time, a decision was taken, why don't you look for the technology from other countries? And then we were looking for the technology, and nobody was ready to come because five countries had the technology. Finally, Russians came forward and a MOU was signed. So initially they will deliver a couple of hardware, and they will also tell us how to realize the engine in this country. And finally, the technology transfer, the realization technology transfer could not take place. And we got a couple of hardware for the initial GSLV, but the mission management systems, basically the equipment bay was developed by us, and we used those things and had almost 6 flights with that hardware. Then it was in the year 1995. In fact, 1993, we were all sent for technology acquisition. Technology means don't think that it is the design technology, it is the only hardware realization technology. But that itself, due to geopolitical reason, we were thrown out of the country, and we had to come back and start our own program in the year 1995, and we started the development. And cryogenic, why it is so complex? It gives better performance, but then very complex because the propellant is at minus 253 degrees centigrade hydrogen. First of all, producing such a low temperature propellant itself is very difficult. And storing that temperature is, under that situation, is very, very difficult. And hydrogen is an explosive nature, so one has to handle very, very carefully. And you know, such a low temperature, all gases will solidify. So we have to have ultra clean environment. Then like that, lot of complexities are there. This temperature, when we say minus 253, please understand, from ambient, 30 degrees centigrade, water is in the water form, liquid form. And when you go to 0 degree, everything will become ice. And imagine with 0 degree, if you stand on ice, how much time you can stand and what will happen, you understand. Same if water is boiled, another 70 degree, you increase. 100 degree it will boil, you put your hand inside, you will understand what that 70 degree difference is. Now from 30, we have to go to minus 253. And under that situation, hydrogen will be in the liquid form that has to be used. In fact, ice itself we cannot keep, it will immediately melt, and such a low temperature how to maintain. And we have to develop lot of system. One of the things is to storage the very low conductive vessels we have to develop. 10 power minus 6 or minus 8 watt per meter Kelvin is the equivalent conductivity of the vessels. What has to be developed? You know, the conductivity of stainless steel is 20 watt per meter Kelvin. This is 10 power minus 7. And then one of my teacher, Professor Sarenge, once he asked, hey, this 10 power minus 6 or minus 7, can you give a feel of what that number? We could not explain properly. Then with a simple calculation, he proved, you know, our thermos flask, if you keep water, hot water, maybe some 25 or 30 hours, it will be in the hot form. Or solely after 48 hours, it will lose its temperature, it will become close to ambient. Now, if you assume you are having a vessel with that type of conductivity, if you store coffee, one can serve, by mathematics, you can prove one can serve coffee for the granddaughter's wedding. That is the type of conductivity, 10 power minus 7, what we are talking. And so it is very, very complex. And now, dear friends, we have taken to 1995, the project was approved. So much development has taken place. Finally, the cryogenic upper stage for the Mark II vehicle, we succeeded in the year 2014. 19 years, and the journey was very tough journey. So many setbacks. We have learned from that, and we have moved. And today, till today, we have realized 7 stages. And the 100th launcher, when we launched, this was the vehicle with the 11th cryogenic upper stage. It went successfully. Now coming to the next cryo stage for the Mark III vehicle, the upper stage is a cryogenic stage, which is 3 times thrust-wise higher compared to the Mark II cryogenic stage. That is 7.5 ton engine, here 20 ton engine. And the propellant loading for Mark II is 12.5 ton, 12.8 ton. Here it is something around 28 ton to 32 ton. So that is the type of thing. And this is Mark II cryogenic stage. At least we had some knowledge based on the discussion with Russian and based on our technology acquisition. Sketch information was there we used, but here everything was our own development from scratch. We have gone and we have succeeded. I want to tell you one thing. A country which was denied this technology, today we are having, to our credit, 3 world records in this development. First world record is we have conceived the engine and subsystems, everything was tested, and then we have integrated and we are going for the engine level test. Engine level test to flight, successful flight, the minimum time taken by any other country is 42 months, and people have taken up to 15 years. And in the CAS, in fact, we have taken more than 12 years for the Mark II vehicle. Here, I think your PRL Council chairman, Kiran Kumar sir was the chairman. And of course, before that, Radhakrishnan sir was there. We both, and I was the project director, and Mr. Somanath was the LPSC director. We put a ambitious target of, what was the target? We said 24 months. Knowingly, somebody has taken minimum time. The developed countries have taken 42 months. And when we put this target, everybody in ISRO and outside the country, they were laughing on us. They were thinking that the 10th standard fellows, without knowing, they are putting this type of target, this type of loose talks were going on. And dear friends, today it is history. In 28 months, we have succeeded and we are having one world record. Second world record is to succeed in this type of thing. Generally, people make 10 hardware, 10 engines and put through a lot of tests. Then only they go for the flight. And our country, we cannot do that type of things. We put a target, only 3 engines. First engine will do the engine level test. Second engine will do the stage level test. Third engine will do a high altitude test. Same engine will little bit will modify, will go for the flight. I still remember when the proposal I presented in IAC in Beijing, I was ridiculed by the international community. They were asking, are you joking in this forum? 3 engines you are going for flight. Then when somebody is asking how to manage, I still remember I gave a reply because I was so much disturbed. I told, whatever answer we are going to give, you will not accept in this forum. We will come back with the successful flight data after 2 years. And today it is history. Only with 3 hardware, we have gone for successful flight. This is the second world record. Third world record, the full credit goes to Mr. Kirankumar ji, because we are having a 5-ton hydrogen and 28-ton oxygen. Everything, a stage is realized, and we are moving to the test stand. Test stand is around 1,200 crore worth of test stand. If you handle properly, it will work properly. If you don't handle, if it explodes, the test stand will be out. And under that situation, generally people won't say they move. They do lot of experiments. Little hydrogen load, understand safety, and little more. And people take almost 7 to 8 months, and carefully then only they authorize the test. So we were running shortage of time. Already we have put a target of 24 months. So we gave a proposal from the project. We will not do any experiment directly go for the flight. Even our own seniors, people were telling, I think we are doing blunder mistakes. Probably when the proposal was put, it was told, Narayanan, you have not understood anything on cryogenics. The statement was also made. And then it is our chairman, then Chairman Kirankumar sir, strongly believed on the team. And he told, if the team is confident, I am clearing. And we have done a lot of modeling simulation. And today, dear friends, I want to tell, against the international standard of 7 to 8 months. And we did a stage hot test for CUS after 14 months in the test stand. This test we have done in 34 days, and we have got a world record, which no other country has done, and no other country is going to do this also. So this is a third world record. With that, we have succeeded. Now, coming to third cryogenic stage, which we have recently realized, a human rated stage. Human rating is improving the margin, improving the redundancies, and we have done this one. This stage is already realized, and we have delivered for the Gaganyaan program. And now we are working on improving the Mark III payload. You know, the Mark III right now, 4,000 kg to the GTO is the capability. We are working on 2 systems to improve from 4 ton to 5.15 ton without increasing the cost of the rocket. And the lower stage, the core stage, right now it is a L1 ton stage, a storable stage. We are developing a liquid oxygen kerosene-based propulsion system powered by a 200-ton thrust engine. And this engine, you can understand, I think you all understand, there is a pump which is pumping the propellant. Pump outlet pressure is something around 650 bar is the pressure. You can understand what is the type of complexity associated with that. So we are in the process of development. And in fact, yesterday, I am happy to report to this audience, it is yet to be given to even press, the powerhead article without the thrust chamber is successfully realized, which is something around 3-meter height article, moved to test stand. Right now, the test stand activities are going on. And this is one of the propulsion system we are developing. Maybe a couple of years, we are going to succeed. And then upper stage, we are going to put C-32 stage. Thereby, the payload will be increased 25%. Then the semi-cryo stage, whatever I told, it is having a lot of advantage compared to a storable system, eco-friendly and cost-effective. But then the complexity is a little more because of the high pressure levels. And this is the article, what you are seeing. This is the article which is realized and just sent to the test stand. And next propulsion system is liquid oxygen and methane. And compared to oxygen and the kerosene, you all know, I don't know, the youngsters may not be knowing. Kerosene stove, how many people have handled? No, we have studied in the kerosene lamp only. So I understand so much of soot formation, fumes, everything will come. But compared to that, the methane system is having a lot of advantage in terms of performance, in terms of restart, in terms of soot formation, lot of advantages are there. We are developing this propulsion system. In fact, the entire world, a lot of developments are taking place. And to our credit, we conceived, to understand the technology, we conceived an engine and we have put through the test until 7 tests were done. All were successful. With that, the government has given clearance for developing an engine with 110-ton thrust level. And you all know we have got recently approval for our next generation launcher. And this launcher, the capability is 1,000 times more than the SLV-3 rocket. SLV-3 is only, it can place 35 to 40 kg in the low Earth orbit. This can place 30,000 kg in the low Earth orbit. this vehicle height is almost 93-meter height and lift of mass is 1,000 tons. And it's a new vehicle. Here, the first stage and second stage, we are going to use locksmith system. First stage will have 9 engines, second stage will have 2 engines, and upper stage is a cryogenic stage, and there will be 2 strap-ons. And then this engine development, right now the design is completed, and we are going ahead with the development program. Next important thing is the next propulsion system called air-breathing propulsion. You know, for operating the engine, we need oxidizer and fuel. So we carry both oxidizer fuel from the ground. Imagine, and oxidizer mass is almost 70% compared to fuel mass. Imagine we don't take oxidizer and we carry only fuel, and atmospheric air if you use, and then use the fuel. That is the propulsion called air breathing propulsion, but there is a small problem. I think today my friend has done a good thing. He has not put any lamp for lighting the lamp. You know, whenever the lamps are kept for lighting, you all may be thinking that chief guest or the guest of honor or directors are so privileged to light the lamp. I don't know how many of you are aware. Whenever I am the chief guest or some function, when you light, the tension what I am having, you will not be knowing. Because the moment you light, you should succeed and it should not quench. If it quench, as per the religious mother, this one, people say it is a bad omen. So immediately it has to happen. And imagine when you light the lamp, there is a fan, somebody has forgotten to switch off the fan. You know, nobody can succeed and the chief guest will be struggling. You know, some function it happens. Even without this also, you will be struggling, and then they will be under tension. You please observe now onwards, the hands will be shaky because the director PRL, when he comes, he wants immediately it should light so that he has succeeded. And the chief guest, he feels immediately it should, but then it will not happen. And sometimes it will quench. Then when you quench their tension, now the air here, it has to enter with Mach number 6. Under that situation, you have to ignite. I think the house, you know, how many times when you switch on the stove, the first attempt, it will be really succeeded. I think our women employees are so lucky. They are well experienced. They succeed 90% time. But we are that not good. Whenever I have attempted 50%, more than 50% time, first attempt I have not succeeded. So now here we are talking about air entry with 6 Mach. Under that situation, we have to inject this one and we have to sustain. And I am extremely happy to report that for that only all PhD, MTech, BTech, gold medal, everybody is working, you know. And we have succeeded in the first attempt itself. And today we are all working towards that further to take this program forward. First time, it is not a small achievement. Please understand. First time succeeding, you are all keeping silent. Okay, doesn't matter. And we have succeeded. Then coming to the reusable engines. Reusable engine, when I am thinking, really one day I was put down by my son. I was in the office, came back 11 o'clock. He was studying 7th standard that time. The moment I came, I was so hungry. I went to straight away, washed the hand, went to the dining table, but he didn't allow me to eat food. He came, he had the mobile, he told, hey, please answer one thing. He showed on video. Video is nothing but the SpaceX coming back and landing fantastically. He told, please tell, when are you going to realize this type of thing? Then I asked, what happened to you? You know what has happened in their school? Somebody has presented. Then he captured this and came and asked this question. You know, recovery of the stage is not very easy to tell, but very difficult. And now, but it is cost effective. Today, we are working towards that type of program. Even that NGLV first stage, we are going to recover towards that. In fact, after I took over as the chairman, couple of experiments, restarting of the engine, throttling of the engine, couple of experiments, we have succeeded. And in fact, it was also reported in the newspaper. So we are working towards that type of activities. Coming to the next one, the spacecraft propulsion system. It has to do a lot of functional requirement. Probably you can read. I will not dwell. Take Chandrayaan 3, for example. We are placed in an elliptical orbit, 170 by 36,000 kilometers. From that, we have to take it to 4 lakh kilometers. Then we have to land. And any communication satellite, it is put generally in the elliptical orbit. And then it has to be taken to the required place. Then we have to maintain in that place whatever disturbance. So it does a lot of purpose. And there are different types of propulsion system, chemical, electrical, and different types of propulsion system. In the chemical propulsion system, what is done is we use oxidizer and fuel and bring it to a common place and burn and generate thrust. And in the case of monopropulsion system, only the fuel will be there by decomposing, it is getting heated up. And then that is heated gas is used for the propulsion, and lot of things are done. Now coming to the achievement of ISRO, Chandrayaan-1, you all know, the PRL team, they immediately will think about that water molecule discovery, all those things. Am I right? But for us, when the launcher completes its job, we have to take it to moon orbit, some 4 lakh kilometer, and something around 10 times we have to operate our engine. Each day is a labor pain day, honestly speaking. If something is not happening, then everybody will look at these fellows and culprits. Who are the culprits? The proper fellows are the culprit. And to our credit, the engine almost 9 to 10 times it was operated and successfully went to moon. And Mars orbiter mission. And Mars orbiter mission, how many of you understand the complexity? 16 crore kilometers we have to travel. And the trigonometry, I think everyone You do a simple calculation when you travel 16 crore kilometers, 0.01 degree error, if it goes, where it will go? It will not go to Mars, it will go some other place. But then we have gone, succeeded, and India is the only country, first country succeeded in the first attempt. You all know it. And behind this success, everybody is responsible. Every system of rocket, every system of satellite is responsible. One of the system is the propulsion system. Of course, first it has taken. Now, how many of you have started your car after 6 months without operating? After 6 months, how many of you have started the car and succeeded without any problem? Can you raise the hand? After 6 months? No, I have not succeeded. Even after 1 month, the battery will not be out and it will not succeed. Here, this engine, it is taking, after 295 days, it has to be restarted and we have to capture. You will not be knowing that day. Everybody was so happily looking for some data, and propulsion fellows were sitting, my God, if it is not starting, entire blame will be on our head. And it perfectly restarted and captured. So that was the achievement of that. And Chandrayaan-3, of course, the launcher placed in something around 36,000 kilometer, 170 by 36,000 kilometer orbit. From there, the propulsion module, which it took it to 4 lakh kilometer by operating almost 10 times, perfectly we did and it went. And then on the day of landing, we were under terrible tension, to be frank, because it is rotating with a velocity of 6,077 kilometers per hour, and we in 19 minutes we have to operate our engine in the opposite direction with all the cameras, inertial system, everything, and you have to bring it to rest. And if it is not working properly, it goes here and there, And the propellant is also not just like that car, we cannot load whatever we want. So very optimally only loaded, and it has to perfectly do. And perfectly the propulsion systems took it to moon orbit and landed successfully. You all would have seen that firing, how the thrust was reduced. And continuously when the mass is coming down, thrust has to be reduced. First time we have put the throttleable system and it perfectly worked. And today the team has got really great standing on this type of development. And not only that, I think this I am not going to dwell. After landing, all of a sudden we had a fantastic idea. I still remember myself and Somnath sir. We were in Sriharikota, we were discussing, so much propellant is left out inside. Why don't you simply lift and place in some other place? The satellite team is not at all interested. Project director, he told what? Because the problem is we have succeeded. Now you lift, that time if it tilted, it tilts, then everybody will tell it is a problem, And they are not sure whether this engine will operate or not. If you declare an engine is not operating, if it is developing some thrust, there are so many engines, and if it tilts, the mission is considered to be success or failure. Somebody will write very bad. But then we took a bold decision. I still remember myself and the past chairman took a bold decision. We were coming from Sriharikota, and here a lot of confusion was there. People were not interested. Some people were interested. Finally, he went to the house. He told Narayanan, I will go to the house and come, you go. I went there, and then people are telling to me, some people wanted to operate. Why we have to do this? Who is there? Some people? We only wanted to operate. Okay. And then I kept silent. If I tell, the people will be throwing me out. Before chairman comes, if I tell we are the people. And finally, dear friends, it is history. perfectly we operated the engine. Initially we tested, then we perfectly lifted, placed in the other place. Of course, it is not only the propulsion system, lot of algorithms, so many validation, and it is history. We have successfully accomplished that thing. Plus the module which took it to moon, that was also brought back to Earth orbit. Thereby, the Chandrayaan 3, I don't know how many of you are aware, the original objective of soft landing is done with 1/3 cost of the project. And coming to Aditya L1, this is yet another important mission. You all know India is the 4th country having today a very successful satellite in the orbit, L1 orbit. But then I was the Mission Readiness Review Committee chairman for this mission, where we have to clear satellite and launcher, everything together. And you know, the MRR chairman, before going for the meeting, we used to have small discussion with the project directors, what it is to understand. So Nigar Saji, project director of the Chandra, the Aditya L1, I discussed, I asked. So here the purpose is, the function is, the satellite, the launcher will put in the elliptical orbit, Earth or elliptical orbit, somewhere around 22,000 kilometers or so. From there, 15 lakh kilometers we have to travel. And a lot of disturbance will be there and we have to go there. I asked a simple question, Madam, how much, the satellite is supposed to work for 5 years. And I asked, Madam, can you tell how much propellant margin you are having? She was telling, sir, 10 kg margin. You know, this is equivalent to what? A car is going from Ahmedabad to Kanyakumari, and we are asking, you know, what is the average speed? Everything is calculated. Petrol is put in this one, and some storage is also there. It is equivalent to having 1 kg petrol margin to go from here to Kanyakumari. It is equivalent to that. And then, you know, as a MRR chairman, what type of tension will be there? I told, what is this for this mission? 10 kg propellant margin. So first, we improved the propellant margin by lot of means. We're reducing the guidance margin, lot of innovative approaches, adjusting the entire mission planning. And today, dear friends, the engine is perfectly taken to that 15 lakh kilometer, and it is revolving. You know, what is the propellant left out there? Margin available. The satellite can work more than 10 years, you all know. So that is the propulsion system, what it has done today. And SpaceX, you know, January 16, this is a historical day, January 16, 2025, probably we have to get credit from the country equal to Chandrayaan 3 launch. But we were worried whether it will dock or not. We are not given big advertisement. And otherwise, the subject is equivalent to that only. And you all know, 16th January, we had successfully docked. Of course, a lot of experiment has to be done. There are a lot of things has to be done further. But India becoming one among 4 countries successfully docked. Towards that docking, lot of things are there, algorithms, sensors, then cameras. But one of the important systems is the propulsion system. Perfectly, it has to work the way we want in a pulse mode. And that is the system what you are seeing on the right side. And it has done its job perfectly. And coming to next propulsion system called electric propulsion system, we use in the satellite generally chemical propulsion. And if you use electric propulsion system where you heat, rather ionize some of the propellant using the electricity or electrical energy, it can generate something around 6 times efficient performance. 6 times efficient performance means if I translate in terms of payloads, you know, a 5-ton class satellite, we are having something around maybe 1000 kg is the useful payload. To place 1000 kg of useful payload, we have to build a 5000 kg satellite, which is having 40% propellant system. Same useful payload can be placed by a 3.5-ton class satellite. So right now, we are in the process of developing the electric propulsion system. In fact, Valyamala, the final phase, the test is going on, and maybe 2nd or 3rd quarter, we are going to demonstrate this, and we are going to be one among few countries having this technology. And now, coming to the future programs for the JAXA, the Chandrayaan 5, you all know, and the mass of the lander is going to be something around 6,800 kg or so, much higher than our Chandrayaan 3 lander. So for that, we are going to develop new engines. The numbers are given here. For Chandrayaan 3, we used only 800 Newton thruster, 0.8 kilonewton. We are going to develop 2 engines. One is 4 times of the Chandrayaan 3 engine with the throttleable system. Another one is 2 times. And this system is going to be under development. Then coming to the Chandrayaan 4, you all know it is a sample return mission. For accomplishing this, again, we have to develop a lot of new systems in terms of propulsion. Then we are working on advanced propulsion systems called nuclear. In nuclear, very easy to understand. I told one equation you would have registered in the mind. Performance is root T by M. Is it clear? Root T by M. And imagine when you fire liquid oxygen and hydrogen, the molecular weight, if it is completely banned, it will be 18. But we use in the optimum way, molecular weight will be something around 16. Instead of that, assume hydrogen alone is heated and the molecular weight is only 2. So root T by M, that instead of 18, the number 2 will come. You know how much performance will increase. So we are working on this type of systems to heat the hydrogen using the nuclear system. And then this is just in the study process. And coming to the Gaganyaan program, lot of things. One is the Mark III vehicle has to be developed with the human-rated propulsion system. Sir, how much more time? 5 minutes? Fine. I will try to complete within that. Then the vehicle takes to 170 kilometers. From there, we have to take it to 400 kilometers and we have to bring them back safely to some level. Towards that, there are new propulsion systems which are developed, demonstrated, and the vehicle propulsion systems are also totally human rated. Human rating means increase the margin, improve the redundancy, make it more reliable. So those things are already done. And another thing is to demonstrate the crew escape system. We have conceived and designed a new vehicle, and I think you all would have seen the test vehicle demonstration for the first time. We got the opportunity to fire a liquid engine from the core, and this is also developed. And BAS, wherever, say the system is like this. Wherever a new satellites are built or scientific satellites are built, the PRL cannot be kept away. You have to give some payload. Same way, whenever we build a new system, new propulsion systems are still developed. That is the place we stand. So here also we have to develop a lot of systems. Then human landing on moon. This program is already on. At least you should understand what is the type of vehicle we are talking. Our Mark III vehicle height is 43 meters and lift-off mass is around 640 tons. This vehicle lift-off mass will be something around 2,000 ton, will be the close to 2,000 ton is the lift-off. 3 times of Mark III is the lift-off mass. And there will be 3 stages. Each will have 575 tons of propellant loading. And there will be a second stage, there will be upper stage. So we are in the process of conceiving and developing. And of course, there are private players. They are in the game in the initial phase. Like our 1967, they have come to that level, and right now they are progressing well, and we are also hand-holding. And ISRO future program, you all know, I think I'm not going to dwell on that. Each program, we have to develop new propulsion systems. And another one is SARB system. Here, you can easily understand, there was a time, if you have to travel from here to Trivandrum, we were traveling by only, most of us were traveling only by train, spending some 60, 70 hours, and we were enjoying the travel. Then it started traveling by aircraft. Initially, we were enjoying, but nowadays it is really boring, 4 hours travel. And somebody has to go to USA, some 20 hours travel, it is too tedious. Now imagine, you have a engine which will take off like aircraft and bring cryogenic rocket engine, you can reach USA in 4 hours. So that is the engine what a schematic diagram is put. I have put some teams to study this type of thing, but then long way to go. And another thing is, when we talk about that crewed mission to moon, we are also thinking of developing high thrust engine to a level of 300 tons. Today, the liquid engine what we are having is maximum thrust is only 80 tons, and we are developing 200 tons. And 110 ton is the locksmith engine, and we are also thinking of developing 300 ton. Thereby, I know I have exceeded the time. To this audience, the time is very, very important. But then, a propulsion development starting from 1967 to now, how many years? 67 to now. So many years, 33 plus 25, 58 years of development and accomplishment. If Anil is asking me to talk in 40 minutes, it is impossible, I know it. And I told my colleagues, please get me only 30 slides. They told, sir, what are you talking? At least 33 plus 25, 58 years, 58 slides minimum will be there. That is the number of slides. And I know I have exceeded the time limit. Doesn't matter. This gives the overall propulsion roadmap of this country with respect to launch vehicle and satellites. Whatever I have talked, everything is there. And coming to the summary, when we started the launch vehicle and spacecraft game, we were not knowing, we know only Deepavali rocket, and we were not having much idea. In fact, you can ask the solid propulsion people who developed in the initial phase. Deepavali rocket reliability was much better than those days solid motors. My boss used to say 90% it will explode. This is what he used to say. He used to say, Narayan, I am not joking. He used to say at least Deepavali rocket, those days, Sivagasi rocket used to reliability is more than 50%, but this reliability was less than 10%. And from that humble beginning, today we have built a capability for solid propulsion, air storable propulsion, LOX methane propulsion, and cryogenic propulsion. The technology was denied to India. Everybody knows if you master the technology, then only we are in the game. If you don't have cryogenic propulsion, India will be only half of the present stature, I know very well. And that is why the technology was denied. And today, everywhere we have mastered. And in summary, the propulsion system, along with other systems, plays a very key role for access to space and space operations. And in that, India is second to none. With that, let me conclude. Thank you. Jai Hind. So now you are controlling the time. I am ready to take any questions, but you will decide how many questions, how much time I have to stand here.
Yes.
No, don't think that chairman is standing. You don't worry.
Yes, sir.
You think that one speaker is standing, and then you decide.
First of all, thank you very much, sir, for this exciting and elucidating, informative Vyakhyaan, which is really, first you started with excellent, it's a big bang. And you started off with right from, simple cars or, solid propulsions to liquid to cryogenic to how we are succeeding or how we have succeeded in several firsts, several accomplishments that we have done, and also how we are better prepared to take on the challenges as posed, that is there in the plan for us. Thank you very much for that. And yes, there will be a lot of questions, but I'll take a couple of questions. Yes, maybe Nirbhay, one. Please keep your questions short. Thank you.
Maybe one or two questions. Otherwise, Anil will be under tension. Already program is running out of time. Yeah, I know it. I have seen the time.
So it was very nice lecture. Actually, I heard before you on propulsion system, Hattan sir, I have heard. So I used to hear that he's very good deliverable. He's giving his lecture delivery, but it was very interesting when you delivered. My question is, sir, we are developing semi-cryo engine. So soon we are going to switch on the methane based. So semi-cryo, what will be mission lifetime actually? Because it will be again.
No, actually, this semi-cryo we are going to put only for the improving the payload of Mark III vehicle. And Mark III, as long as Mark III is there, this will be there. And then the new vehicle will have the other system because there we are planning to recover the first stage and other things. So
Semi-cryo will be retained in Mach 3.
Mark III,
Okay.
yes.
Okay. Just one last question.
Yeah, okay, fine. With that, I think we'll wind up. That will be. Otherwise, we are running shortage of time because I have taken more time.
No, it was really enjoyable. No, thank you very much for this wonderful talk. And before we conclude, I'll request our director, please come and felicitate our speaker and Dr. Narayanan. So please come, please.
Okay. Before
Okay.
before we conclude, the talk is over. Now I am coming to the second part of this one as Chairman ISRO, because for the first time I have come. I have got two requests for you people. First and foremost, as I told, after I took over, I went around the country to take the blessing of the people. I request all of you to bless the organization to grow to greater and greater heights. Because, you know, that in ISRO system, it is not the director or chairman which matters. It is the teamwork which matters. So unless we work as a team, we cannot do great things. So I request all of you to handhold and work as a team for us to take the organization to greater heights. That's the first request. Second thing, whenever you pray, at least some 1 or 2 seconds, you think about our organization also, so that we all will succeed together and contribute for making this country as a developed country before we celebrate 100 years of independence. Thank you.
Okay, now we move on to the next event just to converge and conclude the session.
Thank you, sir, for giving me this opportunity of presenting the vote of thanks. On behalf of the Director PRL का Amrut Vyakhyaan Committee and the entire PRL family, I thank today's speaker, Dr. V. Narayanan, Secretary Department of Space and Chairman ISRO, for accepting our invitation and delivering the 101st Vyakhyaan of our popular and brand PRL का Amrut Vyakhyaan series. Thank you very much, sir, for accepting our invitation and providing a very informative Vyakhyaan on propulsion systems and launch vehicles and satellites. Truly, it is ignited our 101st Vyakhyaan series, and definitely we will propel towards completing our second century. Thank you very much, sir. And I would like to say that in a very simple and humble words, he has taken us through a complex journey of our propulsion systems, where we stand proudly today. And we should feel very proud, and not only that, it increases our responsibility. Thank you very much, sir, for that nice illustration of the journey of propulsion systems. Now, I thank our director, Professor Anil Bhardwaj, for his constant encouragement and continued support for keeping this series of Vyakhyans going on so well, even in its second innings. I thank our Dean, Professor Pallam Raju, Chair, Amrut Vyakhyaan Committee, Professor Nandita, and Dr. Lokesh, Co-Chair, and other members, Dr. Bushit, Dr. Vineet, and all Vyakhyaan Committee members and others behind for all their constant efforts. Most importantly, lot of thanks to all our participants and viewers who have joined us live through WebEx and YouTube today for this Vyakhyaan. With this, we come to the end of this marvelous episode of our Amrut Vyakhyaan. It's now time to sign off from PRL. Please do join us for our next episode for another exciting and interesting Vyakhyaan. Till then, stay tuned and keep following PRL updates on its websites and social media platforms. Thank you, everyone. Thank you very much. Have a nice day. Jai Hind.